All right, we're going to take a look today at a new device you can put in a circuit, something called an inductor. You'll recognize this as a battery, and then you have a resistor, and then we're going to put just a coil of wire after the resistor, and this thing will be called what's called an inductor. The symbol for an inductor is actually just a coil like this, but I've drawn it a little bit bigger here than you would typically draw it, just so we can kind of see how it works. When you first connect the switch, after sort of freshman level physics, what people would think, or after that level of training, is that, well, why, as soon as I close the switch, current's just going to run, and that the current would just go up to what you would get from Ohm's Law. So from like V equals IR, that the current would just build up to the EMF divided by R. And so you'll get the current just going like this. This is basically what, if you closed the switch, let's say at t equals 0, that you would just turn on the current and it would just start to run like this. Well, it turns out it's not quite so simple. If you take a look at what's happening here, as soon as you close the switch, current, of course, is going to start running around the circuit. And here in the front part of the coil here, the current would, I guess, be going that way, and then kind of that way in the back. And so you can see from that when you first activate the circuit, what we would be building up would be a magnetic field in this coil. And so what would be happening is in the early going here is you'd have upward flux that would be starting to build up or increasing. So you'd have increasing upward flux. Magnetic flux. Well, so the device itself then, since you have an increasing upward flux through the conductor will try to make its own downward flux to compensate. So the coil makes its own downward flux, or it tries to anyway. Downward flux to compensate. Well, you can see that if the coil is going to try to make downward flux, that would be actually trying to push back on the current or have current run the other way. All right. So the coil tries to drive some current backwards. Well, it can't because there's a voltage difference, high voltage here and low voltage there. So current wants to run around this way. But the coil attempts to push current back. Okay. So the coil attempts to push the current backward. Right. So in other words, it applies its own voltage kind of backward against the battery. Okay. So it kind of fights this buildup. So what ends up happening then is, instead of the current just instantly ramming up to what you would get from Ohm's Law, the current has to build up to it, because this thing is really going to be fighting at the beginning while the flux is changing in this thing. So instead, what you actually see is that the current has to build up to that value. We know, of course, if we wait a long time, that really this thing is just a wire after all. And so eventually, of course, you will just get the current that you'd get from Ohm's Law. But you have this dynamic behavior at the beginning where you have a changing flux through this coil, and the coil doesn't like that. And so it tries to fight it for a while. And then eventually things kind of just settle down into what you'd predict with Ohm's Law. Okay? So the upshot here is an easy way to think about how these things will behave. It's in the very short term. You basically treat this like a break in the circuit, because you connect the circuit, it tries to run current, and this thing fights you at the beginning. And so that's why the current basically starts off at 0 and then starts to build up. In the long term, this thing just becomes a wire. Okay? So one little easy rule with playing around with inductors is, in the short term, like in the immediate after you close the switch, just treat them like breaks in the circuit. And then in the long term, things have settled down And so then they just behave like a wire. So these things are really only active when the current is changing, because that would mean that you're making some kind of a change in flux in this thing, and the device itself, the conductor, will respond in order to fight the change, right? So that's kind of the basics with an inductor. We're going to take a look in a second at exactly how you figure out how this current builds up. Now, a quick thing to notice before we continue is that you realize this thing is really just acting when you're changing the current in this thing, because that's when you'd have a changing flux, which would make this thing want to respond and push back. Well, so since that's the case, since this thing is trying to push back on the battery, we say that the inductor itself, it kind of acts like a battery that's wired in the reverse of this one in order to push back on it. And this voltage that it's pushing back with, they call it a back EMF, and the size of that back voltage, so they call it a back EMF, and the size of it is L di dt. So this thing's really only waking up or acting when the current is changing. And so notice in the long term, when the current is no longer changing, this thing is not pushing back anymore, and that's why you get a current that's equal to what you get from Ohm's Law. Whereas at the beginning, the current is changing like crazy, and so this thing is pushing back in really acting or most active at that point in time. So what we're going to try to do now is derive this time dependence. So just remember this build up, that we should have an exponential approach to the current that you predict from Ohm's Law. And so we're going to see if we can derive this equation of this curve, or of this approach, right? So the way to start with this is pretty similar to what we did when we were looking at resistor and capacitor circuits. What you want to do is do a Kirchhoff loop around the circuit, so you have all the voltage changes add to 0. So we'll just do a great big Kirchhoff loop. In other words, we can have the sum of all the voltage changes needs to add to 0. And so let's go for it. Well, the first thing that you see, we'll say we start here and we walk around, you're going to have the battery voltage. Then you get to the resistor, so you'll have a voltage drop across the resistor, and you'll have a voltage drop across the inductor. And that sum needs to add to 0. Well, so we have our battery. The voltage drop across the resistor, of course, is just equal to IR from Ohm's Law. So we have IR. And then on the inductor, we get our new term, this back EMF, which is L di dt. So this thing is really, again, just acting up when the current is changing. So what you notice here is we have a differential equation for the current. And so our goal here is, what we want to do is we want to find like I of t, the function I of t. So current is really the thing that we're trying to solve for. Different ways to approach this. My own personal style is I'm looking for current, so I tend to like clear the coefficient down on the current. So what I'm going to do is divide everything by minus r just to get rid of this. So I'll get this minus epsilon over r plus I, the thing that I'm looking for, minus plus L over r di dt. So again, all I'm doing is just clearing the coefficient of the thing that I want, equals 0. And now what I'm going to do is separate variables to separate and integrate. And so what I'm going to do is, actually let's do this first, just so I'll do one more little line of algebra. Equals minus L over r di dt. All right, so now I'm going to separate the variables. And so what we'll do is I'm going to take this entire right or left-hand side and put it under the di, and then everything else is going to come back over to the left. So in other words, here's di on the right hand side. And what I'm going to do is I want everything with di's over here and then like dt over there. I want to separate variables. So I'm going to bring this whole thing under the di. Just to make it pretty, I think I'm going to reverse the order of these. Minus epsilon over r. Okay, and then everything else I'm just going to herd over to the other side. So let's bring this guy over here. So this will be minus r over L dt. Okay, so we're here. Well, we've successfully separated the equation, and so now we're actually ready to integrate. And so what you want to do is say, okay, well, I start my stopwatch at t equals 0, and I go up to some arbitrary time t, and my current is going to start at 0, and it's going to build up to some arbitrary current I, and then we can go ahead and integrate this and see what we get. So let's do it. Left-hand side pretty easy, just going to be minus r over L times t. Minus r over L t equals, we're going to get natural log of the expression in the bottom, but then evaluate it at I and at 0. So we'll go natural log of I minus epsilon over r. Okay, but then the key is you have to evaluate it at 0 and at I. So a little pitfall here, just don't be lazy about the evaluating at the limits. You need it. And so what happens is you get minus r over Lt over here still. Okay, you're going to have log of the expression with I plugged in here minus log of this thing with 0 plugged in. So you have log of a thing minus log of a thing, which is log of the first thing over the second. And so what you'll get is log of the expression with I plugged in. So you'll get I minus epsilon over r divided by minus epsilon over r. What this is saying is basically log A minus log B is log A over B. And so now what we need to do, we're almost there, we just need to solve this thing for I, and then we'll have an expression for the current as a function of time. Got to exponentiate both sides. So you get e to the minus r over Lt, just exponentiating that side. Exponentiating this side gets rid of the natural log. So you get I minus epsilon over r divided by minus epsilon over r. Right, and then our final move here is we just need to then solve for the current. And so, I think just to clear up space, I might kind of go back up here. Wish I had one more line down there. So let's just wrap this up. So all I'm going to do is multiply the minus epsilon over r over and then add the epsilon over r. So when the smoke clears, you'll get I as a function of time equals, and it's going to be epsilon over r minus epsilon over r e to the minus r over Lt. Okay. Sometimes just to make it look prettier, you'll see it kind of written like this. I of t is just pull out an epsilon over r and then write it like this, 1 minus epsilon over r, or excuse me, 1 minus e to the minus r over Lt. Right. Well, let's see what's going on here. When t equals 0, what's going to happen is that, well, e to the 0 is 1, right? So you get 1 minus 1, you'll get a current of 0, okay? When t equals like infinity, if we just wait a long time, okay, it can just be big, let t be big. E to the minus a big thing is basically 0. And so then what will happen is your current is going to approach epsilon over r. It's going to approach the value you get from Ohm's Law. So this actually is this function, well, either one, I guess I'll just circle this one or box this one. This is this graph that we drew before, or if you graph current against time, it's going to start at 0, and it's going to build up and approach to the value that you would expect from Ohm's Law, or epsilon over r. So that's how you derive the time dependence of the current in the resistor-inductor circuit or an RL circuit.